Hey everybody, I found this interesting problem, and the way I saw it done was done differently than a way that I thought. So I'm going to try a different way using what they call elementary symmetric polynomials. Now we have a couple of initial conditions right here. You can read them, and we're supposed to evaluate x plus y without actually knowing the actual value of x and y. And so I proceed fairly normally here. I expand these right two factors, x plus 1 times y plus 1, to get to this statement right over here. And right here I use the sum of two cubes formula to write down this statement. Notice we have a common binomial factor right here. So that suggests, I'm not saying it's necessarily forced, but to do a substitution. Now these guys are called ESPs, believe it or not. It stands for elementary symmetric polynomials, ESP, elementary symmetric polynomials. And they come up a lot using Vieta's formulas when you're talking about polynomials, trying to find sums of zeros and various other combinations of the zeros. But these are called ESPs, not extra sensory perception, but elementary symmetric polynomials. Now, so again, just to be clear, we are trying, what we're trying to find is actually equal to sigma 1. Okay, let's see if I can manage to make that's sigma 1, okay? Sigma sub 1, folks, subscripts. They're a little cumbersome because of the subscripts, but I'm used to using them. Okay, now, using these substitutions, these two expressions actually become these two expressions in terms of the elementary symmetric polynomials. And you can just take a look right here. There's x plus y. Well, there's sigma 1, right? There's xy. There's sigma 2, and so on, okay? So we're now re-expressing these guys in terms of the elementary symmetric polynomials. And something similar happened right here. This is a little harder to see. You can see right here that x plus y is sigma 1. Okay, so that's what I wrote down right there. But what about this sigma 1 squared minus 3 sigma 2? Well, I'll just write that down. I think I have some space here. Sigma 1 quantity squared is just the same thing as x plus y quantity squared, right? After all, sigma 1 is equal to x plus y, right? So I won't write x plus y squared down, I'll just write the result. So what we get right here is x squared plus y squared Now you would get 2xy, and I'll just go ahead and write that down, plus 2xy. But notice 2xy is the very same thing as 2 times sigma 2. It's just a substitution. So just so there won't be any confusion here, I'm going to circle this and see that's equal to 2 sigma 2. The circled object here is equal to 2 sigma 2. Okay, and now you can see why this became minus 3 sigma 2, right? Because we have a minus sigma 2 right here. Let me go ahead and write it right up there, just so y'all see it. If you didn't, if you already see it, I apologize for slowing you down. But anyway, you can see this is what we're interested in, so we have to actually subtract minus 3 sigma 2 to get the minus xy that we wanted right here. Okay, I hope that made sense. Okay, now, so let's go ahead and move along. Now, so what I did is just expand both of these objects out. I expanded this one out and this one out. It made it easier to see if a substitution would work. Okay, and sure enough, it does. If you actually isolate sigma 1, sigma 2 right here, you get this statement. You get this statement right here, and then you get all this. And I'll let you guys verify that, but it's not worth me mentioning every single step there. You can see it there. Now, when you multiply it all out, you end up with a polynomial totally in terms of sigma 1, okay, which is indeed what we're trying to find, right? We're trying to find sigma 1. Sigma 1 is x plus y, right? Now notice here that we have this constant term, 7999. It's an awful large number, and you're going, what do we do about this? You guys have all heard of the rational zero theorem, okay? And that's what I'm doing right here. And there's some results from number theory that say that all you have to do is check up to the square root of a constant to determine the prime factors, the constant in the polynomial, and that's what I'm doing right here. The square root of the constant term is less than 90. Okay, and that's not hard to see. 90 squared is 8100, right? So it's definitely less than 90. And so, y'all, I checked all of these primes. It's real clear that 2 does not divide, 3 does not divide. 2, 3, 5, just by inspection, are not factors or divisors of 7,999, right? It's not as clear, but you have to just do all this by hand, okay? And anyway, all of these numbers, and you can verify this. This part is time consuming, between 5 and 10 minutes at least, if you do it by hand, maybe more. But what this, you've seen this notation here, does not divide or is not a factor of, is what that means. Okay, so but it turns out that that 19 does work. Okay, 19 does. In fact, I'll just write out the result rather than bore you with all the arithmetic. But what we get here, let me get the pencil working again. What we get right here is 7,999. 7,999 is equal. Turns out that 19 is a divisor. And when you divide 19, this all can be done manually. It's just I certainly don't want to waste the video time with that. But you get 7,999 ends up being 19 times 421, and those are both primes. And you can also check that 421 is prime using the square root result. I won't bore you with that, okay? All right. So that's kind of good news. If this were a bunch of divisors here, like if this was a huge prime factorizations with a lot of exponents, we'd have tons of divisors we'd have to check. But as it stands, we only really have to check one. We have to check one, but one clearly is not a solution here, right? One's a divisor of anything, right? Now you can see that 421 would be too big right here. 421 cubed? No way, right? 421 cubed would overwhelm all these terms. So the only possibility is 19 here. And sure enough, if you come up, and I'll just write this down. If you substitute 19 cubed, and I'll write this out, 19 cubed in right here, okay? And then plus 3 times 19 squared, dot to connote multiplication there, 3 times 19 squared. Okay, and then what do we got here? Plus 3 times 19. Okay, we got 3 times 19. And then almost done, ladies and gentlemen, 3 times 19 minus 7,999. That does equal to 0. Now, I'm not, again, I don't want to mess around showing you the arithmetic, and I don't think you want that either. But so that is our solution, folks. That means 19 is the solution. That means x plus y is equal to 0. In other words, we've just shown, or well, sort of, but we've just shown that sigma 1 equals to x plus y equals 19. Okay. And that is the final answer, folks. The way it was done, there's probably better ways to do this. I just kind of like working with elementary symmetric polynomials. But the answer to the original question is that x plus y is equal to 19 without knowing the values of x and y. Okay, hope you enjoy.